Hi, my name is Dr. Mehdi Khan. I'm a PhD doctor. I did my master in electrical engineering from Sweden, and I was working on biomedical device design and terahertz device design. And afterwards, I did my doctor of engineering from USGC, China. And I worked in the Chinese Silicon Valley for some time and designing some chip design. So today, I'm going to talk about the equivalent transformation in circuit analysis. That means how can we make a very complex circuit a simple way to solve the circuits, very complex circuits, and then we can use some theorems like superposition, Thévenin, and Norton theorem, and solve the circuits easily. So, um, uh, first of all, the content is going to start with the electrical quantities, some basic, then circuit model, and we're going to talk about the superposition theorem, and then we're going to talk about the Kirchhoff voltage law, Kirchhoff current law, and voltage divider theorem, which is a theorem, linearity, and linear circuits. We're not going to talk about the non-linear circuits. Then we're going to talk about homogeneous superposition, which includes linearity, and then lastly we're going to talk about the Thévenin and Norton theorem. So first of all, I'm going to talk about the electrical quantities. So an electric circuit is an interconnection of electric components in which energy may be transferred among the various elements within the circuit. A single component, may be classified as it is an active component or it is a passive component. So normally when we talk about active component, we can talk about voltage source, current source. They are active components because they can give energy. And the passive component is like a resistor which cannot give energy but it can reduce the energy. This is we can call a passive component. So normally, now I'm going to talk about the circuit model. So normally the model of there are like two type of circuit models. One there for like ideal active devices like voltage and current source, like you can see on the left side, and the and it can and the voltage can be defined as the plus minus terminal, and the current will have a direction on direction side. So normally why we have this thing, because the current is a measurement of the flow of the is the rate of flow of charge through a circuit. That means flow of energy through a circuit. That's why we make a direction. And for the voltage is the electrical pressure potential difference between the two terminals, or it's called voltage, or we can in old time we call electromagnetic force, EMF. So this is we call voltage, and there are two type of voltage. One is dependent voltage source, which we can see on the scale side, on the downside. This is a current with a scale. It is depend on other variable. This voltage, it depends on other variable. The other thing, which is a circle one, which you can see, it is an independent voltage source. You can see this is where it is in a circle way, which is not dependent with on other variable. It has its own voltage. This is what we call voltage independent source or current source. A resistor is the opposition to current flow present in all conducting material. It resists the current flow. And capacitor inductor, it is kind of a nonlinear devices, and it use like a passive and active components. And now I'm going to talk about the superposition. So normally a superposition, a voltage is what? The voltage across or current through an element in a linear circuit is the algebraic sum. It is the algebraic sum of the voltage across or through current that element due to each dependent source acting alone. It will act like alone. So what normally it means? It means all the independent sources are replaced by the internal resistance, which means with the voltage, it can become a short circuit. That means R is equal to 0. And for the current source, it can act as like an open circuit, which means R is equal to infinity, very high resistance. So this is we call superposition. So there is one more thing, and the Kirchhoff voltage law, the Kirchhoff current law. What is Kirchhoff voltage and current law? Voltage and current law. So it is like the algebraic, like we say sum of loop, sum of all voltage around a closed loop is 0, where voltage drop can be assigned as positive and voltage rise can be assigned as negative, which is a conventional way. But you can do as an unconventional way, which means rise can be assigned as positive and vice versa. And on the right side you can see a linear circuit graph. That means it will have the same voltage, same current. This is we call linear. So like it having the same things. And on the right side you can see a voltage divider theorem. You can see how can we calculate the voltage divider to make the circuit easier to calculate the output voltage. As you can see, so we put V out, and which make the resistance on the parallel side from the output side to the ground side, we make it R2 divided by R1 plus R2 in V in. In this way we can easily calculate the output voltage by using this theorem. And now we're going to use some circuit, a simple circuit which have a voltage and resistance R1 and R2 with a nodal equation, which is node defined as E, and with a current source. And in this PowerPoint, I will use this circuit, the whole to explain the superposition, Thévenin and Norton theorem, so that we can make it easier to understand people. So let's think about, we can write a node equation. So if you see from the node side, so you can see E minus V divided by R1, because if it's from the node side, it can see plus minus voltage, the resistance is plus minus, and the source on the E side is negative. So it means E minus V divided by R1 plus, because E at the node side, the resistance is on the parallel side, so we can say plus E divided by R2 minus the current is equal to 0. This is, we can say, a linear equation. And if you can see, notice the linear equation E, voltage and current. There is no E, V, or there is no voltage multiplied by I term in the linear circuit. And again, I'm going using the same equation where you can see voltage R1, R2 with a current, and we already write this equation previous slide, like E to the north side minus V divided by R1 plus E divided by R2 on the north side minus the current is equal to 0. This is the linear equation. So if we rearrange and make it matrix, you know R is a resistance, the conductance is equal to 1 over R. So if we do this thing in this way, you can see on the right side, we can write this equation as 1 by R1 plus 1 by R2 and multiply by, because there is on both sides there is E, we make it out, and that become a node voltage. The voltage at the node, what is the voltage at the node, is equal to divided by V over R1, because that becomes a linear sum of sources plus I. It will tell you the linear source V over R. And then we can rearrange the equation in a matrix way, or we can write like this thing, this whole thing with using voltage divider, which I already defined you. How can we write a voltage divider? And then we can write E, the node voltage, is equal to R2 divided by R1 plus R2, if we see, and then multiply by V, the voltage, plus R2, R1 divided by R1 plus R2 current. This is we can say a linear equation. If you see down, you can see a linear voltage E is a linear node voltage is equal to alpha V1, some constant V1, constant V2 plus constant current, constant V2 plus. This is we call linear equation. So we have a linear equation. This we can call this is linear. So if we have a linearity, definitely we're gonna have a homogeneous because it's linear, and we can use superposition. That means sum of everything. We can also easily sum that thing because it is linear. So normally linearity, if you can see from here, there's a black box, and if you can see on the left side, there is a constant value x1 and x2, some variable x1, x2, with a box inside. The output will be y, some answer. So if we sum up down, and we can add some constant with some variable like constant x1, constant x2, then we will have a constant at the output as well, which means it will be multiplied. It will increase the power. If it is positive, if it is negative, it will decrease it. So it will have a linear superposition constant value at the outside. So again, we're going to talk about superposition. We have a two black box. Okay, then let's think like this is a matrix. Like we can write same like before, x1 a1 plus x1 b1 and x2a plus x2b. The output will be ya plus yb. This is what we call linearity. The output will be sum of all, and the output will be sum of all equation, like ya plus yb. This is we call homogeneous superposition. This is we not called non-homogeneous because this whole thing is linear. Again, we can specify superposition like in a voltage way, like you can see on the left side, which is V1 0, and down is 0 V2, and we can on the downside you can see we can make a matrix V1 plus 0, 0 plus V2. The output will be Y1 plus Y2. Because this is a homogeneous superposition, very easily we can solve it and we can easily sum them. Let's go for some examples so that we can understand this thing. And like I told you before about superposition method, which is respond to each source, and it should be independent source only. This is very important. Independent source only, acting alone. Like I told you before, the voltage can be acted as like a short circuit, and current will be as like an open circuit. The short circuit means resistance is equal to 0, and open circuit means the resistance is very high. This is we call superposition, as I already explained before. So back to the example, like we have this thing for before, like for linear and this thing, which have one resistance and two resistance, and with a nodal node voltage and a current. For now we can use a superposition method, like we already talked, adding them together and what will happen. So here we go. Like I told you before, we will like V acting alone. That means we make a short circuit, and we can make a current open circuit. So we can see on the left side V acting alone. That means V only acting, and we make a current as an open circuit, and we make a voltage divider formula, and nodal voltage will be R2 divided by R1 plus R2 V. And on the right side you can say I acting low. That means we can make a voltage as a short circuit, and then we can have equation of a current as a nodal current R1 R2 divided by R1 plus R2. Then we can sum it. If you can see down, E is equal to nodal voltage is equal to nodal current plus nodal voltage is equal to, we can add these two resistance and voltage, R2 divided by R1 plus R2 voltage plus R1 plus 2 R2 current. This is we call superposition sum, and we can easily solve the equation circuits. This is a demo which we talk about. On the left side you can see one constant voltage that's shown one DC line, and other is a sinusoidal. So what will be the output? The output for a superposition and linear will be sinusoidal plus DC, because that is what we call superposition. So it will have the same thing, that the input is DC and sinusoidal, the output will be DC and sinusoidal. So it will not like will be unsinusoidal because it is a linear equation. So there is other methods to solve the very complex circuit, like we can talk about. There is an arbitrary network. It has so many sources, so many voltage sources. We can replace it with one voltage source, which is a theorem, and this theorem we normally call a Thévenin theorem. So what Thévenin theorem means? So, and we can use this Thévenin theorem in superposition. So let's talk about the Thévenin theorem. The Thévenin, the presence, the reduction of a complex current to very simple form whenever the primary focus of the interest is on the external behavior of the complex circuit. So it applies to resistive circuit, states that all effect of an linear circuit external to reference terminal can be completely predicted from a model consisting of a single ideal voltage source in a series with a single resistance. That means we can replace voltage with a logical shock and with the equivalence resistance. This is what we call voltage Thévenin theorem, where we can make equivalence resistance with all sources making add them together. So this is what, like you can see from here, there you can see where we have a Thévenin voltage and Thévenin resistance, or we can say equivalent circuit of all resistance. We make one circuit to solve the external element, external source. So normally you can see from here, so this is the Thévenin method, where you can see there are so many sources and resistance with this thing. We can equivalent, like on the right side you can see, we make it with one voltage and one series resistance, and then we can this thing easily solve the external network easily by making them equivalent of one resistance and one voltage. That makes make it very easy. And this is one example you can see from here. We have the same examples which I've been explaining again and again. So if you can see, we can make a parallel resistance, which with the theorem we can say equivalent to series resistance. We make a Thévenin or Thévenin resistance. Then how can we solve this equation? Easily. We make a current is equal to V, which is the voltage source, minus V Thévenin at the which is divided by R1 plus R Thévenin. So this then make our circuit very easy to solve other behavior. And this is where you can see we can say V Thévenin can be equivalent to R2 and I, because this is parallel. And same thing for the resistance, that become simply R Thévenin is equal to R2, because the current is acts like a open circuit, so which become R Thévenin is equal to R2. So this is a graphical representative. You can see V Thévenin then can act like the open circuit. So V Thévenin is the open circuit. This you can see at the point at the open circuit, and then we can see open circuit I becomes 0, and and for the short circuit the V is equal to 0. Then we can easily make V is equal to V Thévenin plus R Thévenin I. So there is one more Norton method, which is for the Kirchhoff current law, where we can say Norton theorem, in which this is opposite to the Thévenin theorem, where we put a series. Here we can put a parallel. So we can have, like we can say for the Norton theorem, we can say it applies to a resistive circuit. State that all effective of any linear circuit external to two reference terminals can be completely predicted from a model consists of a simple current source in a parallel with a single resistance. The current is replaced by the Norton current, as you can see on the right side, and parallel to the equivalent circuit Norton R. So this means we can make a very complex circuit which has so many sources with a one equivalent current source, with the R Thévenin is equal to R Norton's resistance to the parallel, and then we can easily solve the equation by writing the Ohm's law, I is equal to V over R. So today I talk about some superposition, Thévenin theorem, linearity, Norton theorem. So how can we solve the complex circuit and make it easier to solve the circuit? Thank, thank you very much. Thank you very much.